illustration here. So this is clear, like what is descriptive, what is inferential. So when the description statistics means when we are describing by collecting, analyzing, and like visualizing the data. And inferential statistics means when we are concluding something from taking drawing a sample from the population and concluding something about the population itself, then it is inferential statistics. Okay, so let's see some more examples. So here I have taken some examples. So if you see the mean salary of random sample of 60 school teachers in 2015 in INR is 1,10,500. So now if I tell this where does it belong, whether it is a descriptive statistics or inferential statistics. Now if you see, we are just describing data, like there is 60 school teachers and we are taking the mean of the 60 school teachers salary. So there is nothing we are concluding over here. It is just a description we are giving. So it is a descriptive statistics. Now again, if I say the median rating of Avatar movie from 50 reviewers on a scale of 1 to 5 is 3.5. Now, if I say this, make this statement, there is no conclusion I am making as such. I am just describing this data, like I have taken a data of 50 reviewers and I have drawn the median out of it, and I am saying that it is 3.5. So again, this is a descriptive statistics. Now, what about the third one? Based on a survey, the mean weekly hours spent in phone by teenagers in India is 50 hours. Now, if I see this may seem that, like my previous examples, these may fall in descriptive statistics. But if you see it, like if you read this line, you will understand that entire population of Indian teenagers, if you are making the survey, it is not possible, right? So you have drawn some sample out of it, like you have done the survey on some random teenagers, and you are inferring that on the Indian, like on India as a whole, correct? So on the entire population as a whole. So you have drawn the survey on a random sample, and you have done some testing. You have found out that the average hours spent is 50 hours weekly. And then you are inferring that on the entire population. So that is something called inferential statistics. So this is an example. Again, if I say like the last one, this is like very much clear because I am predicting here something like in 2030, India's rainfall is expected to be 673 millimeter in the month of June. So here I am predicting for the year 2030, depending on some historical data. But here I'm doing a prediction, or I'm inferencing something, or I'm concluding something. So again, this is inferential statistics. So this is clear from the examples, like what falls into descriptive, what falls into inferential. Okay, now let's understand what is normal distribution, because before we dive into central limit theorem, this concept is very, very important. So this is the official definition given, what is a normal distribution. It is also called a Gaussian distribution after this, like the scientist who have discovered this, that is Carl Gauss. It is also known as a bell curve because it has a shape of a bell. Now, what is it? It is a probability distribution that is symmetric about the mean, showing the data near the mean are far more frequent in occurrence than the data far from the mean. Okay, so this is the official definition, but we will understand deeper meaning of it, like what it stands for. Now let's see some characteristics. What are the characteristics? The characteristics is the normal distribution is a proper term for the probability bell curve. So as I already said that it is also known as a bell curve. In a normal distribution, the mean is 0 and standard deviation is 1. Now this line is very, very important. So just remember these lines because we will see this line. We will see this happening in our examples later. So the mean is 0 and standard deviation is 1. And it has 0 skew. That means skew is a measure of symmetricity. That means it is symmetric curve. It is a symmetric curve. And a kurtosis of 3. So kurtosis is again the measure of peakness. So 0 skew means it doesn't have any skew, like it is not a left side tilted or right side tilted. It is just symmetric about the mean. Normal distribution are symmetrical, but not all symmetrical distributions are normal. Now this line is also very important, and I will explain in this line in the examples I will illustrate later. So all the normal distributions are symmetrical, that is true, but that doesn't mean that all symmetrical distributions are normal. Many naturally occurring phenomena tend to approximate normal distribution. Okay, so let's dive into normal distribution. Now here there is an illustration. Let me just little bit, I think it is visible for all. Okay, so if you see that mu stands for the mean of the distribution here in the first curve, and standard deviation means like 68.2% of the data lies between mu plus standard deviation and mu minus standard deviation. So this is the calculation, or this is a number which is given. 95.4% of the data which lies between mu plus 2 sigma, that is twice standard deviation, and mu minus twice standard deviation. And 99.7% of the data that lies between mu plus thrice standard deviation and mu minus thrice standard deviation. Okay, and one more important thing is that for any symmetrical distribution, mean should be equal to median should be equal to mode. So all these three descriptions should line in, or measures should line in the same line, that is mu. So this is very, like this curve it's easily understandable, like what is a normal distribution and what are the values which is lying between mu and the standard deviation, the mean and the standard deviation, first standard deviation, the second standard deviation, and the third standard deviation. Now, a practical example. So practical example can be the marks. So if you see that most of the people, like this is what, this peakness is what, this is nothing but the frequency distribution, the frequency, the number of people occurring here. Okay, so the people having the average marks mostly, like high. So this data is falling in this blue zone. So like most of the people will be having the average marks. Then following by, like the people who are lying in the left tail and the right tail. So in the left tail, like it is followed by low marks, then very low marks, and then high marks and very high marks. So we can understand from this. So we can say that 68.2% of the people who has the average marks, then 95.4% of the people who will be having this, like lying under this zone, like having some low marks, then average marks and high marks, and 99.7% of the people who will be lying in this zone. But we have to remember that the area of the bell curve under normal distribution is equal to 1. That is, the probability is always equal to 1. It cannot be greater than 1. So the probability is always equal to 1. Okay, so the area under this bell curve is 1. Okay, so let's understand. Okay, so this is the formula. Now, if you see this formula, please emphasize on this term, x minus mu by sigma, because this is going to be important. Okay, why this is going to be important? Now I will explain, like come to the things, like what is the normal distribution? Why not all symmetric distributions are normal distribution? Okay, now let's understand this. So this is our symmetrical distribution. Say like we have a median, we have a mean which is we signified by mu, and then we have standard deviation which is signified by sigma, and likewise we have drawn this bell curve. Now if I have to draw a normal distribution on it, or if I have to replicate this curve as a normal distribution, now you have to remember that point which I have shown in the characteristics, that the mu should lie in the 0, that is a mu equal to 0, and standard deviation should be 1. So that is actually when you are normalizing this curve. So this is what it means. So that means my mu should lie in the 0, that is my mean is the 0, and my standard deviation is 1. So this is actually where I am normalizing this curve. And I am normalizing this curve based on certain score or critical measure, I can say, which is also known as Z score. So this is a formula which is given, like Z equal to x minus mu by standard deviation. Now, what does it mean? Let's understand this with an example. Okay, so let's take that our heights are given, like a set of heights is given of a class, and let the mean be 66 inches and standard deviation is 2 inches. So this is very clear, like the average height in a class is 66 inches, and it can be like plus minus, if you deviate it, it is like 2 inches. Okay, so now if I draw a bell curve on this, so this is my bell curve where my mean is lying in 66 and 2 inches is my standard deviation, so it is like 66 plus 268, again plus 270, again plus 272. Likewise, I have drawn the bell curve. So this is very easy to understand. Now this curve is symmetrical, right? but it is not a normal curve. Why it is not a normal curve? Because our mean is not lying at 0, right? Then what I need to do, I have to normalize this curve. So in order to normalize this curve, I have to find out this magic number, that is z-score, correct? So if I have to find out for any data point, say for any height which measures around 67 inches. Okay, so let's take that x equal to 67 inches. So where it will lie here? It will lie somewhere here. So this is 67, fine, good. Now if I have to normalize this curve to a normal curve, what I will do? I will find the z-score. So what is my z-score here according to the formula given? If my x is 67, I am putting 67 here. My mean is 66, so mu is replaced by 66. And standard deviation is 2, so I am replacing sigma by 2. So calculating it, I am getting 0.5. So this is my z-score, what I'm drawing in my normal distribution curve. So this is 0.5. Here it lies between 0 and 1. So this is pretty simple, right? Now we have a z-score table also where we can find the probability of having this score, correct? So now if I find that z-score value, actually like the probability of having z equal to or z less than 0.5, then everything falls in the left side of this score actually gives you the probability. So what does it mean? We will see it. Okay, so just remember that if I say that z is less than equal to 0.5, that means everything falling under the left side of this curve for this score, from this score, is giving you that probability. So the area of the curve falling in the left side of this code gives you the probability. Okay, so now let's understand this. So let's understand with a problem. So this is our Z table, and this table you will find in Google. So if you just search with Z table, you will get in Google, you will get in the statistics books. It is very easily, like available everywhere. So if you want to find the Z score, suppose I say that Z equal to 0.63. Now how we will find the Z score for Z equal to 0.63? Now this is how you can find out. So you can find out first the Z values over here in this column. Okay, so where is my 0.6? So here is a 0.6, and 0.63 means I have to add up more 0.03. So here in the column, you can check for 0.03. So this adds up to 0.6 plus 0.03, that is 0.63. So this intersection value will be my probability. So this is my probability for Z equal to 0.63. Sorry. Okay, so if Z, I say that Z less than like this area or this probability of a value having less than equal to 0.63, then this is a probability that is 73.57%. So this is how you can see the Z score. So this is clear? Okay. Now let's move on, dive into the next topic. So let's see an example to understand this better. Okay, so this is an example I have taken, and these examples, like these kind of examples, you will find like ample in the Google. I have also taken from Google, so you can search in Google to find the sums like this to understand like what is Z score. Okay, so now this is the problem. Now the problem statement is your local pizza shop claims their large is at least 16 inches or it is free. So if they are not giving 16 inches of the pizza, then they are giving it free. Their pizza is normally distributed with mean as 16.3 inches and standard deviation as 0.2 inches. What's the probability of getting free pizza? What's the probability of getting lucky with pizza over 16.5 inches? And what's the probability of getting pizza between 15.95 and 16.63 inches? So we can see there are three problems basically. Let's solve the first one. So what's the probability of getting free pizza? Okay, so let's see. So now this is my curve. Basically, it is a normally distributed curve. The mean is lying at 16.3. Now I have to find the probability of this area lying less than 16, right? Because if the pizza size is less than 16, then only I will get it as free. So what's the probability of getting free pizza means? The area in this, the area, shaded area, like less than 16, correct? Okay. So now if I see this, the z-score, now you will find out that this is my z-score which is coming. So if I put 16 here, 16 minus 16.3 and 0.2. So standard deviation is 0.2. So this is my z-score minus 1.5. Okay. So if I find out the probability from my z table, so this is the probability which is coming. So I have drawn the z table also. That is, I have to find out this shaded area which is less than minus 1.5. And so this, my probability of x less than 16 should be my equal to probability to z less than minus 1.5. So if I find out from the z table, minus 1.5 is 0.668. Now you can see this from the z table. I have opened the z table. Let me see over there. Just 1 second. Sorry, is my screen visible?
Yes, yes.
Yeah. So what is my z value here? Z value is minus 1.5. So if you go here, so if I let me check the z table. Okay, so minus 1, first I will search from here, minus 1.5. Okay, and there is no other denomination, so I will just take 0.00. So this is 0.668. So this is my probability, 0.0668, that is 6.68%. Okay, so this is how we can find out the values from the z table. Let me draw this again. Okay, so this is the value which is coming for the probability. So the probability of getting a free pizza is can be easily found out like it is 6.68%. Okay, now let's see the second problem. What's the probability of getting lucky with pizza over 16.5 inches? Okay, so now this is my area. Now when I will be having, like I have to find out the probability of more than 16.5. But again, this curve is not normal curve, right? We have to normalize this curve. This is a symmetrical curve, but this is not a normal curve. Okay, so we have to find out the probability x greater than 16.5. Okay, now what is the z-score here? So to normalize the curve, we need to find out the z-score. So again, x value is 16.5. My mean is 16.3 and my standard deviation is 0.2. So this z value is 1. So this is my curve now. So any area greater than 1 should be my probability. Now I already told that z-score probability means the entire left side from that score. Okay. And also I have told that the area under the entire bell curve is 1. So we have to find out z value 1. So that is z value 1 is 0.8413. If you find in the z table, you can find it. So z value, like probability of z equal to 1 is 0.8413. And I am negating it from 1 because the entire probability is 1 and I have to find the left side, right? So the left side I have got 0.8413. I have to find this shaded area. That means 1 minus 0.8413. So it will give me the complement of the z-score, of this z-score. So then I will find out this shaded area probability. So that is 15.87%. So likewise, you can very easily solve these problems with the z-score and normalizing the curve, basically. Now let's see the third problem. The third problem is getting pizza between 15.95 to 16.63 inches. Okay, so this problem 2 is also solved. Let's go to the third problem. Okay, now this is my data now. So where I have to find this probability of this, like under this shaded zone, right? The minus x value is 15.95 and plus x value is 16.63. Okay, so this is my probability. This should be my probability while x is lying between 15.95 and 16.63. Now this is not normalized. So I have to normalize this curve. So to normalize the curve, I have to find out the corresponding Z score also. First for 15.95 and then for 16.63. So my minus Z will be minus 1.75 because I have put 15.95 minus mean by standard deviation, the same formula. And I am putting for the score also, 16.63 also, I am finding the Z, that is 1.65, which is giving me this curve. So now this is my normalized curve where my Z is lying between minus 1.75 and 1.65. This is fine. Now we have to just find the probability of this shaded zone from the Z score table. So that is very easy. So we can find first 1.65. And then we can find for minus 1.75. And like the probability of 1.65 is 0.9505. And probability of minus 1.75 is 0.0401. So we have to just negate this red zone from this orange zone. As I have said, like the probability is given to the left side of the score, right? So if you find for minus 1.75, it is all the left side of this score. That is a red zone. That is 0.0401. And if you find 1.65, it is the entire left side of the score. That is this zone, like the entire orange zone. So orange zone plus red zone, the entire zone left to this score. So that is 0.9505. So to get only this orange zone, we have to subtract 0.0401 from 9505. So we get this probability. So that is 91.4% times 0.4% times. We will have the pizza between 15.95 to 16.63. So this is our third problem. Okay. So now we have some idea on the normal distribution. Okay. So let's dive into central limit theorem. Okay. So central limit theorem states that when a large sample size has a finite variance, the samples will be normally distributed and the mean of the sample will be approximately equal to the mean of the whole population. So what does it mean? Like if there is an entire population and I am drawing random samples from it. Now there is a number for that samples. The sample size should be significantly large, which is either greater than or equal to 30. So this is a number, magic number, which is given in statistics. So the sample size should be sufficiently large, which is around equal to or greater than 30. So provided this figure, if we are drawing the random samples from a population, then first the samples will be having normally distribution. That is what it is assuming or it is concluding. And the mean of these samples. So if I take S1, S2, S3, S4 like that, if I take n number of samples, the mean of these samples will tend to be same with the mean of the population. So that is what central limit theorem states. Okay, now let's understand this with an example. Now this is a formula. Again, this formula is looking little bit similar to the Z score. If you see here, like X minus mu, only difference is instead of standard deviation, we are using here standard deviation by root over of n. So n is a sample size over here. That is like whatever sample size you are drawing from the population. Okay, so let's understand this. Now we have a population where mu is the population mean. Now this is very important and try to pay the attention over here. Now mu is a population mean which is given. Standard deviation is a population standard deviation which is given. Okay. Now I am drawing some random samples from it. Okay. So I have drawn sample S1 and its mean is mu1. Understand like this. I have drawn sample S2 and its mu is mu2. Like mean is mu2. Okay. Likewise, I am drawing some random samples. Okay. Likewise, I have drawn sample N and whose mean is mu_n. This is fine. This is understandable. Okay. Now, provided the sample size is, as I said, that it should be greater than or equal to 30. So this is something like specified in this theorem. Okay. So this is a significant amount of sample size. Now, if I draw these samples, okay. First of all, central limit theorem states that they will have a normal distribution. So that is first thing. That is my S1, S2, S3, Sn all will be having a normal distribution. What is the second assumption? Second assumption is the mu of the each sample, the mu1, mu2, mu3, all will be equal to the population mean. So that is the second assumption. So if the sample mean is mu x, say this mu1, mu2, mu3, I have denoted as mu x. So this is my sample mean. Then my mu x should be equal to the mean. Mu, that is means the population mean. And my standard deviation should be equal to the standard deviation, population standard deviation by square root of n, where n is the size of the sample. So this is simple, like mu x is the sample mean and standard deviation x is sample standard deviation. Okay, not the population standard deviation, sample standard deviation. So sample standard deviation is given by the formula population standard deviation by square root of the n. That is the sample size. So this is clear, right? So this is what the central limit theorem states, that if you draw some random samples and provided the sample size is greater than or equal to 30, like of a significant size, and they are independent of each other, then they will follow a normal distribution. Not only that, their mu will be tend to be the population mean. That is their mean, their average, their mean will be tending to the population mean. That is the entire population mean. And their standard deviation will be the standard population standard deviation by square root of the sample size. This is what CLT states. Now, that is why I told that before we go to CLT, we need to understand a little bit about the normal curve. That is why I explained the normal curve before. Okay. So these are some of the applications. So if you see the sample, like the applications are very wide in statistics for CLT. So if the first one is very important, like if the sample distribution is assumed to be normal, when the distribution is unknown, like you don't know anything about the distribution, whether it is normally distributed or not. According to the central distribution, the method assumes that the given population is distributed normally. It helps in data analysis. So again, it is helping you in analyzing the data because you are assuming that the random samples which you are drawing from the population will be distributed normally. Then the sample mean deviation decreases as we increase the sample taken from the population, which helps in estimating the mean of the population more accurately. That means larger the sample size you take, the more the deviation from the sample mean and the population mean will decrease. That means it will more tend to be equal to the population mean. So there also you can estimate the mean of the population more accurately. Then it is used in a lot many things like creating a range of values which likely includes the population mean. Then in election polls also this CLT is used, calculating the mean family income in a particular country, then rolling many identical unbiased dice. So these are some of the applications which we can see in CLT. And even like it facilitates in constructing good machine learning models. So this is also one important, like application. Okay, so let's see some problems. Okay, now before going to the problem, this is very important. Now, while we put or we state central limit theorem or we apply central limit theorem to a problem statement, we need to see like whether we will use Z-score or T-score. Now there is a lot of confusion, like whether to have a Z table or T table. So like we have a critical score as Z-score, we have another critical score called T-score. Okay, so we call it a Z-test or T-test. Now here is the like the easy way to understand this, whether I know the population standard deviation. So whether my population standard deviation is given. If it is no, then we can use a T-table. If it is yes, then we need to check if the sample size is greater than 30. So this is the number I said, like this consists like this in statistics, this means a significant sample size. So if it is greater than 30, then we can use the Z-test. Otherwise, you can just use the T-test. Okay. So this is a very, like easiest way to understand. You guys can take the screenshot or this is available in Google also. You can just check out it. You will get how to, like understand whether to do a Z-test or a T-test. Okay. Now, let's see some random questions. Okay. Some random examples from the high school mathematics, basically from the high school statistics. Okay. Now I am not going to solve these problems, but I will discuss these problems with you. Like now like how to understand like whether we will do a Z test or T test. Now let's see the first problem. Okay. 20 students are selected at random from a clinical psychology class. Find the probability that their mean GPA is more than 5. If the average GPA scored by the entire batch is 4.91 and standard deviation is 0.72. Okay. So if you see the population mean is given, that is the average GPA scored by the entire batch, that is a population mean, that is 4.91. And standard deviation is also given 0.72. So our first question, is the standard deviation of the population known? Yes. That means now we have to check what is the sample size, correct? So the first question is solved, that is the standard deviation is given for the population, right? But now name the next question, what is the sample size? Okay. So what is the sample size here? 20 students drawn at a random. Okay. So 20 is less than 30? Yes. So if it is less than 30, we are going to do a t-score on this. Okay. So likewise, we have to get the t-score. So t-score formula is same as z-score. Only thing is that for the central limit theorem, we are applying x minus mu by standard deviation by square root of the number of the sample size, basically. The number of the data drawn. Okay. Now let's see the next example. Now I will explain t-score, like how to see the t-score in the table also. Now let's see the next example first. The average weight of water bottle is 30 kg with a standard deviation of 1.5 kg. If the sample of 45 water bottle is selected at random, from a consignment and their weights are measured, find the probability that the mean weight of the sample is less than 28 kg. Now, if you see the average weight of the water bottle is 30 kg, it is given, the population mean is given, the population standard deviation is given. So whether the population standard deviation is known to you, yes, it is known. So 1.5 kg is given. Now the next question, what is the sample size? So if you see here, the sample size is 45 water bottles. That means it is greater than 30. So the things are clear now, like this is a problem where we are going to use the Z-score. We will do the Z testing, basically. So now see, because the sample size is more than 45. Now the rest of the things are very clear. So if you just find that what should be your mean weight of the sample less than 28 kg, means you have to find out X less than 28. The reciprocated Z score also we have to find out, and likewise you can find the probability from the Z table. So this example we have seen in the last example also, likewise you can do this example, this problem. So guys, you can take a screenshot of this, but you can find similar problems in this, there is abundance of these problems found in the Google. You can find in the high school statistics books also for the central limit theorem problems. Okay. Now, next one. The record of weights of a female population follows a normal distribution. Its mean and standard deviation are 65 kg and 14 kg. So mean is given for the population. Standard deviation is also given 14 kg. That means standard deviation is given, means we need to check the sample size. Now, a researcher considers the record of 50 females drawn at a random. That means 50, that sample size is 50, correct? So if it is 50, that means it is greater than 30. That means definitely we are going to do the Z testing. Then what would be the standard deviation of the chosen sample? So here you have to find the standard deviation. You can put the formula and you can get the standard deviation. So this problem is pretty simple. Okay. Now let's see some other factors which we will consider while doing the t-testing. So our purpose today is to understand central limit theorem. Until now, I have discussed central limit theorem, normal distribution, because normal distribution is very important to understand central limit theorem. And central limit theorem also I have explained. Now I am going little bit, like the related topics, like Z test and T test. And with T test, there comes some other, like parameters which we need to check, that is confidence interval. So let's look at it. Okay. So this is a confidence interval. So what does a confidence interval mean? So for a range of a sample, on a range or on a sample, if you are performing certain experiment again and again, like repetitive experiments. And the same data points, you are seeing that the percentage of the data points lying between the lower limit and you got an upper limit, and the percentage is always like 95% is occurring, like the same data points is falling in the same limits. Okay, so then you have this 95% confidence that your set will fall in this lower limit and this upper limit. Like the probability will be falling into this lower limit between this lower limit and upper limit. So that is something called confidence interval. So when you're doing a repetitive experiments on a set of data, and you are getting like some percentage like data falling under the same lower limit and the upper limit, then that is the confidence you are getting basically when you are doing again and again the same experiments. So that is what tells you that 95% confidence you have that you will get this probability between this lower limit and upper limit. So that is what confidence interval means. Now it is very important when we determine the t-score, because there is a value called alpha, which is called significance level. So this red zone basically, like tells your alpha value. So from lower limit to upper limit, this is your confidence level. And this is a formula. So Ci x plus minus z into s by, so s is a standard deviation, x is a sample mean. So these are all given, x bar is a sample mean. And you have to multiply with the z score or the t score. So this is a critical score, you need to multiply based on the sample size or the other parameters. So these are there, you will get the confidence interval. That is your lower limit and the upper limit. So let's see some examples, how to do it. So the steps to find out the confidence interval. How? Identify the sample problem, choose the statistics like sample mean, etc. that we'll use to estimate population parameter. Select a confidence level. So you can select any of this confidence level like 90%, 95% or 99%. Okay. Find the margin of error. So most of the times it is given, but if it is not given, this is a formula for margin of error. That is a critical value. Critical value means your z score or t score into standard deviation by the square root of this number. Okay, so this will give you the lower limit or the upper limit, the confidence interval basically. Okay, so let's see some example. Now, so this is an example like this is a sum again from the high school statistics. You will find many examples like this. A random sample of 10 UFC fighters were taken and their weights were measured. The mean weight was found to be 240 kg. Construct a 95% confidence interval estimate for the mean weight. The standard deviation was 25 kg. Find the confidence interval for a sample for the true mean weight of all the UFC fighters. Okay, now if you see here, the sample size is 10. That means it is less than 30. So definitely we cannot go for a Z value. So we have to go for t-score. Okay, so let's understand this. Now there is another parameter which we need to find out while finding the t-score, that is degree of freedom. So degree of freedom is nothing but it is the sample size minus 1. So here it is 10. So 10 minus 1, it is 9. Now, your alpha is the significance level, that is 1 minus CL by 2. Why 1 minus CL by 2? As I said in the previous example, the confidence limit, that means the lower limit and the upper limit, the area falls beyond that. That is your alpha. So for the two-tail thing, it is on the both sides. So we are dividing it by 2. Okay, so if you see here, this is my confidence limit. So anything the red zone beyond this, okay, so this is my confidence limit, the red zone beyond this, the red zone basically, it is my 1 minus CL by 2. Why? Because, why by 2? Because if the entire area is 1, so this is my confidence levels or intervals of CL. And so 1 minus CL gives me the red zone, but why by 2? Because it is 2 tails. So for both the tails, we are getting by 2. Okay. So this is the significance level, that is 1 minus CL by 2. Okay, so that is if I take 95%, it is already given, construct a 95% confidence. So 95% is already given. So it is 0.025, alpha is 0.025. Now using the values DF and alpha in T distribution table. Again, this table is available in the internet. Let me just show you. Okay, so this is a T-score table. So if you just search, you will get in the internet. If you see here, the degree of freedom is given over here. Now, according to our problem, the degree of freedom was 9. Okay, and the alpha value is 0.025. So if I go over here, so my degree of freedom is 9 and alpha is for 210, that is 0.025. So I will go here. Okay, so for 110 it is 0.025, for 210 cumulative it is 0.05. Okay, so 9 and 0.025. So this is the intersection point, 2.262. So this is a value I have taken here, 2.262. Okay. So likewise, you can find the values in the Z table and T table. So my T score is now found out. Now the same thing, the same formula. That is, if you have to find the CL, the confidence limit, that is mean plus minus T into the same formula, the standard deviation by square root of N. That N is a sample size. So this is your formula basically given over here. Like putting the formula, you can find the mean was given as 240. So 240 plus minus. So T score is given 2.262 and 25 is a standard deviation, which is again given 25 kg. 25 by root over 10, 10 is a sample size. So it is giving you the lower limit and the upper limit. So this is giving you the confidence interval. So my lower limit is 222.117 and upper limit is 257.883. So this is how you can find the confidence interval with the T-score and even like do the T-testing accordingly. Okay. So these are some of the sample problems I have taken. Let's see like another problem. Okay. So if you see here, the random sample of 50 adult females. So 50 means again, this is a greater than 30. So we will have a Z testing here. Okay. The sample mean is 4.63 and standard deviation of the RBC count is 0.54. So mean and standard deviation is given. Construct a 95% confidence interval. Okay. Interval estimate for the true mean RBC count in adult females. Okay. So now mean is given, standard deviation is given. What is another thing is given is 95% confidence interval. That is also given. Okay. Now sample size is given 50. Okay. Now to find this area like minus Z to plus Z. So this is my confidence interval basically. Now since we are doing Z testing here, so I have denoted it as minus Z and plus Z. So this is my confidence interval also, right? Now this area we need to find out. So this area is given like we need to find out. So now what is this area? This area is given as the probability is 1 plus CL by 2. Now you will be asking like why this formula, like how I have found out this area. Now I have told, right, the entire bell curve area is totally is 1. Okay. Now if you take half of this, right? Half of this is 0.5 and this half is actually CL by 2, correct? So this is 1 by 2 and this is CL by 2. So if I find out the probability of the Z score, like the Z, the positive Z, it should be the entire left side of this Z score, correct? Now the entire left side is what? If I find out the area, that is already this half is covered. So this half plus this confidence limit, that is CL by 2, I can write. So that's why I have written 1 plus CL by 2. So half plus CL by 2, that is 1 plus CL by 2. So that is giving me 0.075. Now I will do the other way around. Now I have done what? I have found the Z score, right? I have found the probability from the Z score. Now here the probability is actually given, like the entire area before the left side of this Z, positive Z is given. Now I have to find the actual Z score from that, from the table. So here if you see the probability is 0.7975. Okay. Now in the previous problems, I have done the opposite way. I have found the Z score, probability from the Z score. Now here actually I have to find out where this 0.975 is existing in the Z table. Okay, so let's search it. So this is my value. This is my probability which has come 0.975. Now let's find it out. 0.975 should be somewhere here. So yeah, so we found it. So this is 0.975. And what is the corresponding Z score? 1.9 and 0.06. So we sum up to 1.96. So this is my 0.975. And if you see the value, yes. If you see the value of this, let me just little bit, yes. So this is 0.975. This is a probability. Now I am searching other way around. The probability I have got, but I need to find the z-score. So this is 1.9 and the 0.06. So we sum up to 1.96. So this is easily understandable, right? So in the previous problems, what we found the probability from the z-score. But here we are finding the z-score from the probability, the other way around. Okay. So here the area means we have found the probability. When we have found out the area, that means we have found out the probability. Now we have just calculated the z-score from it. Okay. So the z-score is 1.96. We found from the z table. Now we have to put the same formula like the values in the formula. So the formula was mean plus minus z-score, that is a critical score we are using here is z-score, not the t-score because of the sample size. So z-score into the standard deviation by square root of the sample size, it is 50. So we are just putting the formula and we are getting the lower limit and the upper limit, which is giving us the confidence interval. Okay, so here till here I will explain, like I explained, I think most of the things, like I explained the normal distribution, I explained central limit theorem, and I little bit explained on the z-test and t-testing also, now which follows the application of CLT basically. So I hope this gives you an insight. I have tried to make it simpler so that everyone understand and have that frequency to grasp this, this theorem altogether. So I hope this gives you an insight. So I will just ask like whether I can take the Q&A on this.
Yes, there are 2 questions in the Q&A part.
How 30 becomes a magic number in CLT? Good question. So that I need to check. Basically, I knew that 30 is a magic number in CLT. That is a significant statistical size, which is, which is given. So we consider 30 as a significant statistical size. How do we decide? Sorry. How do we decide whether we will use z-score, t-score in confidence interval? Do you use table you mentioned before? Yes. So I mentioned the chart before. So let me just go through that chart again since we have some time, 5 minutes time. Okay. So let me just put this. So basically, see, we need to understand that whether the population standard deviation is given. So if you just follow this pattern, you can do it. And you can follow this standard, standard decision-making thing, like whether you will want to use a z-score or t-score. But again, it is based on the decision. Even if it doesn't, satisfy some people, prefers to use the t-score. But I am just telling you the basic rules behind this. So do you know the population standard deviation? If yes, you know the standard deviation, then you go and check that whether your sample size is greater than 30. So if you see in the problems I have taken, wherever the sample size is less than 30, I have used the t-testing. Like I have told that you have to use the t-score or t-testing. But if the sample size is equal to 30 or greater than 30, then I think z-testing is okay. Like you can go with the z-testing. So this is how you can determine. If you don't know the standard deviation of the population, you can use a t-table. So this chart you can take a screenshot, or you can remember also it is, you can find in Google also, it is available in Google. So this is how you can remember and understand. So if the sample size is greater than 30, then you can follow the Z table. If it is less than 30, you can follow the T table. So this is a very simple, decision making thing you can take on Z testing and T testing. Okay. Okay, is there a way to perform this calculation in Python? Yes, there is a ways to perform this calculation. I have some Python notebook which I have done before to calculate t-score. I can show it, but I have to install the launch the Jupyter notebook and all. Why calculate confidence interval? Okay, so for t-testing, it is important that you know the degree of freedom and the alpha value. So for that, the confidence interval, so from alpha actually, it follows that, like, these are all, like associated topics. Like, what is alpha? If you say about alpha, then what is the alpha and what is the rest of the area? So that is your confidence interval, basically. It is your confidence limit. That's why I told about it also. That what is the rest of the area, what is alpha, then it is easier to understand that what is alpha, what is confidence interval, what is confidence limit. So these are all associated things. That's why I explained a bit on confidence interval. Okay. Yeah, this I can share, this notebook I can share. It is in my Git channel. So I can share this. Okay, I think this gives you some insight on CLT, guys.
Thanks a lot, Munmun. On behalf of IT Vidya, I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future. I hope you guys have filled it in the feedback form. If not, I request you to fill the feedback form. If you wish to conduct a webinar or facing any difficulty in registering, connect with us at editor@analyticvidya.com. The recording of this session will be available within 2 days on our YouTube channel, and we will get back with another session of the Data Hour on 28th December. The link is in the chat section. Till then, bye-bye and keep smiling.
Thank you, everyone. Have a great day.